Okay, so I think Timothy wanted to, well, unfortunately, Cynthia didn't feel well, so she couldn't show her example, but I think Timothy would like to start now with an example from last.
Yeah, okay. So thank you again to be there. Are there any questions on the last two parts? So networks and dynamical systems? No, everything is okay? So today we will merge the two parts, and so we will be able to have dynamics on networks. So if you want, the take-home message will be to understand how the jaguar got his spots, is the title of a book or of a novel. So, but before to do this, I will try to make this intermezzo, which is a small warm-up example that is, they say, the simplest in some sense possible dynamical system and network, and show you the interplay between dynamics and topology of the network. And so the example is this random walk on a network. Okay, so what is a random walk on a network? So first of all, you have a network, which is non-directed, so you can jump from A to B, B to A without any problem. It is connected, so if you wait long enough, and this is for you, is ergodic, so you can reach all the nodes if you wait long enough. So there is no pieces of network that is connected from the rest of the part. Then you consider a walker, say a person, can be a mail, can be a virus, can be an email, a photo, and so on, which is on one node. And then each time step, so imagine you have a clock, the walker decides to jump to one of the neighborhood node that is chosen with uniform probability. Okay, and then the question that you ask is, okay, let us define PIT is the probability to find the walker at time t on node I. Okay, so you have this node, this network with hundreds of nodes. You have your walker, each time steps you walk around, and then you will have to know with which probability pi you can find the walker at node I. So in some sense, this is the frequency of visit if you wait long enough. Okay, so the question is what you can say about pi of t. How this answer is related to the structure of the network. Okay, so if you take the same process of random walk, but you change the underlying structure, how this function PIT will change. Okay, so let me just give you an example. This is my network, is made by 7 nodes. This is my agent, which is on some node. And I use, as I told you last time, Aij as the adjacency matrix. So it's symmetric. So Ij, Ji is always 1. And so this is 1 once I and J are connected, and 0 otherwise. And then you have the degrees, Ki, which is the sum of all the neighborhoods. So these nodes are degree 3. 1, 2, 3. This one have degree 1, this one at degree 2, and so on. We already saw this last time. Then, as I told you, with the probability which is uniform with respect to the number of links or neighborhoods, the walker jumps. So he was there, the degree is 3. So with probability 1/3, he chooses one of these 3 nodes. And so the transition probability is given by the existence of a link between I and J, because otherwise you cannot jump, and then divided by 1/Ki. So this is the most simple example that you can have. You sit on a node, you look around you how many neighborhoods you have, and with, say, you throw a dice with as many faces as possible, and you jump on this node. Okay, and then you iterate. Each time you iterate, so you can go back and forth and so on. Okay, then it's easy to write that the probability of finding the walker on node J at time t plus 1 is what? Is the probability to find it at node I one step before, so assume time is discrete variable, times the transition probability to jump from I to J, and then summed on all possible I. Okay, so if which is the probability to be there at time t plus 1, but it's the ability to be or there at times t, or there at times t. And you have to add all these probabilities. Okay. Okay. Once you have this equation, you can write it in compact form with a vector, which is a very huge vector because it has as many components as the number of nodes. And then this equation can be rewritten as P transpose t plus 1 is equal p transpose t. This is just a remark. This is a Markov process because the next step depends only on the present. And so in this kind of Markov process, we work with say row vector instead of column vector. It's just a notation. So that's why we use p transpose at time plus 1. And so if you want to know what happened for time infinity, so for very, very long time, you have to take the limit of this function of vector p t plus 1. If you call this limit p star, then you understand from this equation that p star is a solution of p star equal p star t. So p star is a left eigenvectors with eigenvalues 1.
Can I ask a question?
Yeah.
So this is for a static network, no?
Yeah.
I give an epidemic example. For example, if we consider dengue and the nodes represent villages, and let's say that in one village, everyone at a certain point got infected and recovered. So if this now is representing the dynamic, the possibility that dengue goes to the village, that nodes is being removed. So we would have to deal with a dynamic network.
Okay, why do you say the nodes is removed?
Well, not because of the person. If now the nodes represent the how to say, if now the node represent the network available to the disease to spread, if there are no more infected people, they can be infected. If everyone was recovered and as immune for that year is immune, then we have a network that if now it's not a person but it's a disease. Think about how the disease can spread. So
I understand. Yeah, you can deal also with time-dependent network. The point is that the process can be no longer a Markovian one. Mm-hmm. Because the probability to jump depends not just on the present, but on the past. And there are some strange phenomena that can appear. So imagine even a simpler example where you have the network links are created and destroyed, say randomly in time, and you want to jump. So you have to choose among the links that are available at that point. But then there are several subtle questions that arise. For instance, how long a link lasts? Is it instantaneous or not? If not, how long the jump lasts? So and then how long does the worker stay on a node before to jump? And so we did some work in this direction. I can quote a paper of our group next time because I don't have it right now. But you can do some random work on time-varying network. It's a bit harder, but it can be done. But for instance, in a process like this one, where you don't have memory at all, the fact that you create and destroy links and you wait on each node create a memory. Because the idea is the following: suppose that you are there and these two links are not available, and so you jump there. It's only possible, okay? But if this link lasts long enough, once you are there, the probability to go back is quite high. And so in some sense, the worker remembers for where he came. And so this induces a memory effect. And so this is why it's not Markov any longer. But so this can be dealt with, but is beyond the simple example that I would like to show you today.
We have a question from
Igor.
There's
a question by Igor. Yeah.
Igor?
Can you listen to me?
Yeah, yes.
It's kind of a minor question, but the presence of a dynamic topology in such a network is not a necessary condition for memory, is it? Because you can have a very specific configuration wherein you change the topology without changing the transition probabilities.
Yeah, yes, that's true. Yeah. Also, it depends on the time that one link lasts. If one link is instantaneous, create and destroy, that there is no memory at all, because once you jump there, if this link is destroyed, you don't have memory to go back. So in some sense, if the worker wait on each node long enough, you can lose this memory.
Yeah.
Right. Yeah, but this goes a bit beyond the simple example that I would like to show you with just a static network. Okay.
All right.
Okay.
Thank you.
Okay. Thank you. So as I said, so we have this asymptotic probability distribution, which is a P star, which is so the left eigenvector of solving this matrix. And then you can realize that the solution of this equation is proportional to Ki. So the probability to find asymptotically the worker on node I is proportional to the degree of the node. Of course, you have to divide by to normalize to have a probability. And so this means that the nodes with a higher degree have a higher probability to find a worker over there. So the hub, which is the node with the largest degree, are the nodes in which you can find more often the worker than in other nodes. So you see that there is a link between dynamics and topology. So the topology of the network, this is the hub or the degree, in some sense drives the dynamics toward, say, spending more times on most connected nodes. So there is an interlink between dynamics and topology. Just to, because we will use in the following, you have this equation, you can write P star minus P star T equal to 0. And this operator, this matrix, identity minus T, is called random walk Laplace matrix. So if I write it explicitly, this is the matrix Lij, which is identity minus Aij divided by Ki. So this is a matrix that, so not this one, but some similar method that we'll be using the following. Okay. Okay, now that we have done this small example and I show you there is a link between dynamics and topology, I would like to enter in the real part of my talk, which is the dynamical system on network. So in the books that I quoted last time by Rabashi, also by Newman, there is already a part of dynamics. Here, if you want two more books, I can quote these two. So one is, of course, Dynamical Processes on Complex Network by Rat, Barthelemy, and Vespignani, two from France and one from Italy, now in the US. And this one by Dynamical System Network by Mason Porter and James Gleason, that two quite good book. This one is more recent, this one is a bit older, but they're still good books. So if you want to have an idea of processes on networks, diffusion like random walk and so on, you can have a look at this kind of books. Okay, so let me introduce the dynamical system on a network. So that is the following that I told you at the beginning of my first lecture. So let me talk about neurons and brain. So suppose you have one neuron, so you have one dynamical system, and you make n copies. So you have n identical copies of the same system. So you just index them with some I. So you have the evolution of the vector xi. So the derivative is some function f of xi. So note that the function is the same for all the nodes because it's the same dynamical system. Okay. So there are three main questions. The first one is how to couple this dynamical system. So these copies, these neurons. What can you say about the global behavior of the system once you have chosen a kind of coupling? And then, which is I think the most interesting part, are there some new properties that do not exist once you have the isolated system, but they emerge or are created once you have this system as a whole? So this is the idea really complex system that I show you at the beginning. If you have a system, so the network one, you cannot divide these small pieces, ask what happened in each pieces and then scale up. You cannot do it because once you cut in pieces, you lose the system. And this is the idea of these emergent properties. You would like to show that there are some results that you cannot see once you look at each single system. Okay, so let us try to answer to the three questions. The first one, how to couple them. Like if you want to couple, you have to choose some interaction, because coupling means interacting. Interacting means exchange something. So here this can be again a question, so not philosophical one, but a question about modeling. So if you want two things to interact, you have to change something. They can exchange physically something. So I can go from Brussels to Paris. I bring with me a virus and I spread the virus. So I physically move, even if I'm at the vector of the virus. Or I can send an email. So I don't move actually. I send some photo, something like this. In both cases, you have interaction. But in the first case, it's more a diffusive-like process, because the person or the actor that also interact, he moves, he physically moves across the links. Okay. While if you, in some sense, exchange signals, this is not really diffusion, because of course there are the signal that diffuse, but the stuff that they change or react, they remain stuck on the nodes. So this is a bit difference between diffusing and not diffusing, and but the difference is not so sharp. You can think again that I live in Brussels, but I work in Namur, and so I go from Brussels to Namur. If I stay long time in Namur, then I spread the virus, I think this is diffusion, because I diffuse from Brussels to Namur. But if instead I go from Brussels to Namur, say 2 hours, and then I go back, at the end, it's like I was always in Brussels. In some sense, I send the virus in Namur because of my 2-hour stay. So in this case, if you have some moving back and forth, this is what you say, Stefanella. If you have people that move across district and so on, maybe it's better to model this with interaction instead of diffusion, because people go back and forth. In some sense, they do not have time to react locally, they just go back. So as I say, there is no sharp division between diffusion and not diffusion, and so I would like to consider both, but again, which one to use depends on the model that you want, the question that you have. Okay, so as I said, I will try to show you this diffuse-like coupling, because diffusion is in some sense Browian motion. I see diffusion-like because there is no Browian motion behind. Also this adjacency coupling, where this idea of signal. So I send you information, but I don't move. So in some sense, you become affected because I send the virus, but I will not be any longer there. Okay. Okay. So let now. So the first question has been tackled more or less. So the two other questions I can be put together with this kind of simple question, because in principle there are many other, but I will focus on this one. So assume that once you have the isolated system, they do synchronize. So they all converge to the same equilibrium. Okay. And then suppose this equilibrium oscillates in time. You have this idea of metronomes that they all tick with regular speed, but if you put them on the table or on the wall, at some point they start to synchronize. So this means that because you, in some sense, interconnect the metronomes, they start to synchronize. They start to have a new behavior together. Or you can have a system where everything converges to the same equilibrium. Imagine, I don't know, a chemical reaction where you have 10 times the same reaction. If you put the reaction in different tubes, in each tubes you will have the same equilibrium. So I don't know, concentration of X, Y, and Z. But then if you start to interconnect these tubes with other pipes and so on, maybe you will find another equilibrium that is not the same as before. And so the question is, if you, as a system, do synchronize or maybe convert to some equilibrium, does the coupled system do the same, or does it exhibit a new behavior? And so this idea of a spot on the Jaguar, as I told you before. And so this is a book, a part of a book by Murray. Murray wrote several books and papers about epidemics, pattern formation, geometry, and so on. So you can find also a book by Murray, and there is also this part that I will present now about Turing pattern. And so here is a study on details of I recognize maybe a jaguar, and maybe this is a tiger or a leopard. I have no idea. Anyway, so there are several animals with several tails. Then you can show in the book that you have more this ring-like or spot-like or labyrinth-like or I don't know what. And this paper by Vespignani, Pastor Satorras, is a natural physics paper of I don't know if you can read it, is 2010, so it's already 10 years old paper, where they study this pattern of complexity, is the idea of this emergent behavior because you couple together different systems. Okay, so let's now start this jaguar and the spot, but on a network and not on the skin on the jaguar. So the next step is to assume that on each node, you don't have just one species or one agent, but you have a lot of them. It's sometimes a continuous. So each node hosts a population of agent, and this is what is called metapopulation model, which is an idea which is dated to the 72 by Robert May in the framework of ecology. May wrote this paper, "Will large complex system be stable?" With the idea that he has several islands where in each island you have a stable population of animals. But then if you start to connect the island because I don't know, the sea change levels and so on, then the question is, how will the system behave? Will it be stable or not? And so this the idea of metapopulation is that on each node you have several, so this is some schematic view, several agents or two species or more than two species, and then you have reaction on the nodes, so mathematically speaking, differential equation on a node, and then you have diffusion across nodes. So if you want to partial differential equation in some sense, but yes, space is discrete because space is the number of nodes. Okay, so in the framework that I will display you now, you have interaction on each node and diffusion across edges or links. Okay, so let me start with the sample example of the two. So I assume that once you have the isolate system, all the nodes converge to the same stationary number. Okay, so if there is no network, everything goes to the same constant, this x star I for all I. Okay, and as I assume this diffusive-like coupling. What does it mean, diffusive-like? So if you remember a bit of physics, there is this Fick's law, that tells you that the diffusion is such that you equilibrate the concentration of the two nodes. So I will light my light. Okay, sorry. So in continuous medium, we have this Fick law that tells you that so in this framework, the concentration at node I will increase if there is more concentration in J than I. So it equilibrates, like water, because here is higher, then this go down and this go up. And vice versa, the concentration in I decreases if there is more, say, water in I than in J. Okay, this is kind of low. But then if you take this equation over there, this just means that things again are water. All the water that is in node I goes to all the neighborhood node J. So it should be I and J should be connected. That's why I put here the adjacency matrix. Okay, but if you look closer to this equation, you realize that this part of the sum doesn't depend on J. And so you sum up to xi, sorry, because I remember ki is the sum of ij. And then here you can, here you have xj and xi, so then you can introduce this delta. And so you have sum over j of aij minus k degrees delta ij xj. And so here you recognize again the Laplace operator. It's not exactly the Laplace operator that I showed you before, because this was the random walk was, let me write, random walk was identity minus a, say, oh, sorry, okay, I cannot write. Let me write this way. ij, ki. So in the random walk, Laplace I divide by the degrees, while here in what is called combinatorial Laplace matrix, I subtract the degrees. Okay, so in some sense you have to equalize, I'd say, the water or the concentration in neighboring nodes. Okay, and so you observe that the assumption of diffusing coupling implies that the rate of change of the variable x and node I is just the product L times x. Okay, and so once you have the diffusion, the reaction part is simple. Just add, okay, before some property of this Laplacian, I will add the reaction then. So this matrix has the following properties. Of course, it is symmetric because remember, Lij is equal Aij minus delta Ij chi I. The matrix I is symmetric because I suppose the network is not directed, but delta is symmetric, Ki is a constant, and so this is symmetric. So you can diagonalize, you have real eigenvalues. So this is the first part. The second part is that this matrix sum to zero. Just a computation, because if you write sum j Aij minus delta Ij Ki. Okay, once you do the sum of j of Ij, this is Ki. The sum of j of delta is one only once j is equal to I, so this Ki minus Ki is 0. So this matrix is sums to 0, and this means so that 0 is one eigenvalues, and you can show that this 111 is eigenvector. You normalize by the square root of the number of nodes. Okay. The last part is that this matrix is non-positive definitive. So it means that the spectrum is a question, or is the same end as before?
I guess it's the same.
Ah, okay, because I show a pop-up in my, okay, sorry. So it is non-positive definitive. So this means that you have 0 as eigenvalues, and then you have the spectrum is negative. You can check this simply by taking the scalar. So first of all, if you remember at some point, I defined the matrix M, which is the incidence matrix. And then I show you at that point that if you take a minus the transpose times M, you get the adjacency matrix minus the diagonal of the degrees. And this is exactly L. So L is the product of M transpose M. And then this shows you easily that L is non-positive, because if you take the scalar product of an eigenvectors times L eigenvectors, you replace M with this product, you do some computation, you end up with this, but this is nothing but lambda alpha modulus phi alpha square, which implies that lambda alpha is negative or 0. Indeed, you can prove that the multiplicity of lambda equal to 0 is related to a topological feature of the network. If the multiplicity is 1, the network is connected, it's just one piece. If the multiplicity is 2, then the network is composed by 2 pieces. If it's 3 pieces, and so on. So you have an information about the topology of the network, which is in some sense inside the Laplace metric, inside actually the eigenvalues 0. Okay, so remember in the following, we will use this fact that it is diagonalizable with real eigenvalues, and the spectrum is negative, and there is one which is 0. We will use this in the following. Okay, so now we can put the reaction and the diffusion together. So you have the rate at which, say, the concentration at node I changes depends by some function, which is the isolated system. But then you couple all the nodes with this diffusive like, and then you put a matrix D, which is a diagonal matrix of diffusion coefficient. So this means that species I don't know, go faster than species J, and so on, because not all species have the same speed or diffusivity. Okay, and so the question is, you know that the initial X star is a solution of the isolated system. You can see that X star is also a solution of the coupled system, because if you put X star in this equation, we show in the previous slide that L sum to 0, but sorry, here I put the index J, but indeed this is a constant because all the nodes have the same concentration, and so this is 0. So this means that X star is also a solution of the coupled system. And so the question is the following: assume that X star is a stable. So X star is stable for X dot I is equal to F. So the isolated system converge to all the system to the same values can be can be unstable for the coupled system. So x dot I is equal fxi plus dlx. So can you destabilize your system because of the connection that you put? So this is the idea that that's why the gap got is spots, because what are the spots on the skin of the jaguar or the gap? You have cells that produce some chemicals, pigments, and that react locally. But if the cells were isolated, almost all chemical system goes to equilibrium, which is the thermodynamic equilibrium, so a flat concentration, say a uniform color. But indeed, the cells are part of tissue and they interact each other in the first neighborhood, but also in the second, and so on. And so this exchange of pigments, of chemicals on the skin of the animals can be able to reproduce this diffusive-like coupling. And then Turing showed almost 70 years ago that you can couple two processes that separated, they goes to the same equilibrium because the diffusion homogenized. Here, the reaction also homogenized, but if you put together, they can destabilize and create non-uniform solution. The skin, the pattern of the skin of the jaguar, for instance. Okay, so as I told you, this is the Turing instability phenomenon. So we are asking if a stable equilibrium can be destabilized because of the diffusion. Okay, so as I say, because the equilibrium now is unstable, the solution, so a small error or a small disturbance close to the initial condition will increase in time, and then the system will converge to another equilibrium, which is possibly not homogeneous, because the chance to have another homogeneous equilibrium is very few. So the idea is that if you start close to a homogeneous equilibrium and you are destabilized, you go to another equilibrium that in principle, this is patchy solution that is the skin of the jaguar, if you want. Okay, so let me show all this stuff on a simple example. I took this Bruselator, but first because I'm from Brussels, and second because it's a dynamical system that was used because it's nonlinear system which has some root on chemistry, so it can be used to explain pattern formation. So okay, anyway, it's just a nonlinear system. You can replace it with your preferred dynamical system if you want. So you have two species, U and V, that sit on each node I of your network. You have some parameters, B and C are the parameter of your model, the reaction part. And then you have this du and dv, they are the diffusion coefficient of your model. And then you have this coupling diffusive like as before. So this is exactly the model that I showed you before. X prime I is equal f x I plus d lx I. In the special case where f is the Bruselator and I only have two species instead of generic number of species. Okay, then you can just a small computation. If you remove the diffusion part, you can show that U star and V star, the equilibrium is 1 and B over C. Okay, so this is the equilibrium of your system. You can show this is the only one. There is only one equilibrium. Okay, then because you want to study the stability of this equilibrium, you linearize around this equilibrium. So you put xi is equal to ui minus u star, yi equal vi minus v star. You put this equation, this equation inside your model, and you linearize, and you end up with a linear system. I don't think I have to do the computation, but they're quite easy. Just remember once again that the part that involves Lij sum j, say x j plus u star, gives only sum j Lij xj, because the sum of Lij on the constant is 0, is what we showed before. Okay, that's why here you only have Laplace times x and Laplace times y. The rest, the part is just the linearization, the usual linearization of the system. What I showed you some days ago is the Jacobian. Okay, indeed, you can write the Jacobian matrix, so
Sorry,
B minus 1C.
Timoteo, may I ask a question? May I ask a question right now regarding this centralized action? Because you told us that if you ignore the dispersive term, you're going to have the fixed point to be 1 and B over C, right?
Yeah, but this is true also if you put the diffusion. It's just what I said, that if you're interested, so remember at the beginning I start the isolate system xi equal f of xi, and I say, okay, x star is an equilibrium, so I have to solve f of x star is equal to 0. And so there's yeah.
No, I was just thinking about like whether or not you could have a sort of well, it wouldn't be really fixed point per se, but like you could have a moving equilibrium, like in the phase space. For example, the u dot I equal to 0 solution would be moving in the phase space.
Yeah, of course, yes.
Dispersion.
You can have a time evolution solution. In this case, in the Brusselator, you can also have a periodic solution. But here, I assume that the isolate system converges to the stable equilibrium. So here, I'm just looking for a stable equilibria. In the next part, I think Thursday, I will show what can happen once you have a time varying solution. Okay, but I agree with you.
Nice. All right.
And the Brusselator can have both, can have a stable or time varying solution.
Okay, makes sense.
Okay.
Thank you.
Okay, fine. So I say that here you have this part, which is the Jacobian. So this part here. Then if you want to study the stability, if you remember my first lecture, you have to compute the quadratic polynomial associated to this matrix. Those roots are given by this one. Just second order polynomial, it's very easy. And then you want to, if you want, you can recognize that this part here is the derivative of the linear function with respect to f, the derivative with respect to v, and so on. So you have all these parts. So indeed, the Jacobian, you can rewrite your characteristic equation as lambda square minus lambda times the trace of the Jacobian plus the determinant of the Jacobian equals to 0. And this it's easy because then instead of studying all these kind of parameters, it's easy to show that you have stability if the trace is negative and the determinant is positive. There are not so many choices. Then, of course, the trace is negative means that b minus 1 minus c should be negative, and the determinant, you have to compute the determinant. So in some sense, I put all the dependence on the parameter just on these two conditions, just to simplify a bit the notation. Okay, so we assume that these conditions are satisfied because you want the stability of the homogeneous equilibrium. And then what you do, you now consider the extended system. So you put again the Laplace, the diffusion part. So here, this is my matrix D, which is a 2 by 2. Observe that I put zeros over there. These two terms are called cross diffusion. In some sense, it tells you how X evolves in time. This one means how X evolved in time because of Y. Okay, so for the moment I only took diagonal, so it means that X evolved in time only because D of Xi, but in principle you can have a more complicated diffusive like behavior. Okay, so anyway, let's now work with this one. Remember, L can be diagonalized, so let me write phi alpha is eigenbasis, and then I project my component xi and yi on this basis. So I will have this component xi alpha and eta alpha, and now the terms, the sum Lij xj, if you replace this one, becomes sum over alpha, lambda alpha, xi alpha, phi alpha. Just a bit of algebra. Okay, and once you do this, the equation on the top, if you replace x and y on the projection, and you use the fact that the eigenvectors are orthonormal, then you can end up with a new equation which has been projected on each eigenmode. So observe that this part is the same, it doesn't change, except of course you're not having the space x and y, you have in the space c and eta. But this part is a bit simple because here you have a sum, while now you just multiply by eigenvalues of L. Okay, and so the question is again, you have this second order equation, or if you want a first order vectorial, and you want to study the stability. And so you can write this as a new matrix, say an extended Jacobian that I call J alpha, which is J0 plus these eigenvalues of the Laplacian times D. Okay, and I assume now, because I want to show that the equilibrium become unstable, and the simplest thing is that assume that it is unstable exponentially. So if lambda alpha is positive, then you have exponential growth at short time, while if lambda alpha is negative, you have exponential decay at short time, so the equilibrium is stable. And of course, this small lambda alpha is a function of all the parameters, but more important, of the spectrum of the Laplace. So this is where the network enters. The network enters via the spectrum. Okay, so you have to solve this equation, but you realize that this equation is nothing but the same equation as before. So you have lambda square minus lambda trace of this extended Jacobian plus determinant of the extended Jacobian. And so instability now means that or the trace is positive or 0, or determinant is negative or 0 for some alpha. Okay, so remember, stability is trace negative, determinant positive. So because you want not stability, so instability, at least one of these should be verified for some alpha. Okay, the first one cannot be verified. Why? Because the trace of G alpha is the trace of G0 plus lambda plus times the sum of the diffusivity. But the diffusivity are positive. It's a coefficient, a positive coefficient. Lambda is negative or 0. The trace is negative by assumption, so this quantity is negative. So the only possibility to have an instability is that the determinant is negative, so the negative or 0. Okay, so are you following? Okay, I hope yeah. So now we have to study this condition. I don't know if, yeah. Okay, so you have to study this condition. If you write explicitly what is this determinant, is he has 3 parts. So you just do some computation. Again, it's easy, just take the matrix is there, this matrix, and take the determinant. It's 2 by 2 matrix, okay? It's not so difficult. And then you recognize there is a term which is in lambda square times the UdV. So this is positive, of course. You have the determinant of G0, which is positive by definition, because we assume that X star was, U star, V star were stable. And then you have this part in the middle, but you know that lambda is negative. So the only possibility to have this stuff negative, this part should be positive. Because if this is negative, everything is positive, so the determinant will be always positive. Okay, so you have this first constraint that this special combination of dv times the derivative plus du the derivative is positive. Okay, this is as a special consequence, because if you remember, the trace of G0 is negative. Okay, so this means if you put these two together, you realize that one of this derivative or this one should be negative, because otherwise you cannot have trace negative and this positive. Okay, if both were negative, this is okay, but this is impossible. If both were positive, this is okay, but this is impossible. So it should be one positive, one negative. And so at the end, you should have this derivative, which, if you remember, these are the rate at which U changes because of its own reaction. That is the rate at which V changes by its own reaction. So in some sense, are autocatalysis, self activation, so the production of themselves. Okay, but because they are one positive, one negative, in chemical language we speak about activator and inhibitor. So assume, for instance, that this derivative is positive. This means that the species U is an activator because he activated himself, he produced himself, while V is an inhibitor because he inhibits itself, he decreases its own production. Okay. Okay. This implies also, so yeah, I had some small computation, but it's like it can be done, it's quite straightforward. So if you take again the two conditions FU GV negative, so this is trace, and the other condition is DU, this U, GV plus DV FU positive. These are the two conditions that I just wrote before, and I assume that FU is positive and GV is negative. So let me just do a bit of algebra. So this one can be written, so this one is like the same as minus du absolute value of GV plus DV FU positive. So this means that DV, my V and U are the same, sorry. DV FU is larger than DU absolute value of GV. But if you take this one, let me write here, you have that this is the same as FU minus absolute value of GV is negative, this means that FU is more than absolute value of GV. And so GV is larger. So this means that it's larger than DU times FU, but F is positive. So this means that DV is larger than DU. This is a result that Turing found almost 70 years ago. And then Geyer and Maynard, in this paper that is quoted down here, found again, say, 20 years later. And they show that indeed all the Turing pattern exists because of this constraint. The inhibitor should diffuse faster than activator. And sometimes you have some kind of long range interaction because the inhibitor goes very fast. And once it's far away, it inhibits. And the fact that it inhibits, it creates an absence. And so it creates a void in some sense. And this creates this patchy distribution because the activator is able to produce, but it goes very slowly. So it will not have time to reach the inhibitor and create a gain. And so this creates this patchy solution in space. Okay, so this is one of the results that I would like to show. So this inhibitor should diffuse faster than the activator. And then indeed to show the instability, okay, you can do all the computation that you want, but the simplest one is use some geometry. So as I told you, this is positive. This is positive. And so in the plane where, let me draw here. So remember, lambda is negative, so I put here lambda alpha, but what is important is only the negative part. This is a parabola. This is a parabola which is concave toward the top. So this is something like this. If it is the case, this parabola has a region where the parabola is negative, so where the determinant is negative. While if the parabola is something like, I don't know, like this, then this parabola is always positive. So you will never add this instability. So now the game is to try to understand when such parabolas are of this kind, so where you have these two zeros, or you never meet the axis. Okay, so you can do all the computation that you want. The simplest one is again some elementary maths. You look for the minimum of the parabola, which is so the vertex, and you want that this vertex has horizontal position negative, and it is a negative values. If you do the small algebra, I think is a second year student algebra, then you end up with this condition. So let me remove the parabola. So this is the condition that you find by imposing this, the vertex is negative. Okay, and so if now I put everything together, we have these four conditions. The first two are the condition for the stability of the equilibrium homogeneous. So this is stability homogeneous equilibrium, these two. And these two are the condition for instability of homogeneous equilibrium with diffusion. Okay. And so you see that you have these four conditions together are the conditions that Turing wrote in this very well-known paper that are able to show that you can destabilize or not your system. So let's now go back to the Brusselator. So if you take a Brusselator, you put the terms, the derivative and so on, you end up with this simple equation. The trace is just the sum of b minus 1 minus c should be negative. The determinant is just c, so it's positive. The condition that makes diffusivity and derivative is this one. And then this is the last one, which tells you that indeed you should have, if you want, c larger than b minus 1, which is this. So here I'm in the plane BC. So I fix some parameters du and dv. I don't remember the exact value. And so in white, you don't have pattern, so you don't have instability, while in red, you have instability. So this line here is the line C equal to B minus 1, while this, say, parabola-like line is this part over there. Okay, and now if you take any value of B or C inside, then you will have Turing stability. If you take any value of C and B outside, you will have you will not have Turing stability. One thing is interesting with respect to the question that someone asked before. If you are in this region over there, the equilibrium the homogeneous equilibrium is unstable, but indeed it bifurcates through an off bifurcation. So here you have limit side behavior. So you have homogeneous solution that depends of time periodically. Okay, so this is a part that I will not show you today, but this is important. So here you have Turing pattern. Here you don't have anything. Here you have not Turing pattern because you have oscillating behavior. Okay, let me just show you this. So if you take now a values here, so I take a B equal 4, C equal 5, and the two values of the diffusivity, then you, if you compute the rate, this lambda, which is called dispersion relation, as a function of the eigenvalues, you find this kind of curves, which is negative at the beginning. So it should be negative there because this means that for lambda equal to 0, so for once you don't have coupling, the system is stable, but then this function increase. At some point, it becomes positive. For all these red points here are associated to eigenvalues of the Laplace matrix for which Xi alpha and eta alpha has a positive, say, exponential positive increase. So they are unstable. Okay. While if you take a point in the white region like this, the blue curves and all the dots are below 0. So for all the values that you take for the lambda alpha, you always have this exponential growth, yes, but with a negative exponent, so exponential decay. And so this means that indeed the homogeneous solution is stable also in the case of the network system. So what is the network? But the network is inside lambda. So all the information in the case of pattern or not pattern or about the network is condensated into the spectrum of the Laplace matrix. So an information that can be very complicated to handle because the network can have a scale-free, Watts-Rogers, Erdős-Renyi, whatever you want. All the information is in the spectrum of the Laplace operator. So once you know the spectrum, you know everything about the patterns, if they can exist or they cannot exist. So this I think is a really important result because you can show that in principle, very huge amount of information is condensed into a single value, say 10 values or a small number of values anyway. Okay. So this is the example. So what is a pattern? So of course, in a network, you don't have the beautiful skin of jaguar or giraffe, tiger, and so on, but you have points that got different colors. So here is the example where you have this kind of pattern. So you can show or ui as a function of t, you show that 1 is the equilibrium. So if you remember, u star is equal to 1. So we start very close to 1 and then they bifurcate. Each node reach a different amount of concentration. It is a pictorial view for an Erdős-Renyi network where I took 20 nodes and a probability to have a link of 30%, 0.3. So you have this kind of nodes that are colored. Or here I have a more, say, beautiful picture where you have, sorry, this node is time. So here you have not nodes, is time. Time and this node. So I show with the color code the evolution times of each node. So here is just a function is a color. Okay, but you can see there are nodes with very high concentration. So remember, the equilibrium is 1. You have nodes that can reach up to 2 or 1.5, while you have nodes that can be down up to 1/2. So you have a differentiation of the concentration on each node because of the topology. Okay. And yeah, okay, in the case of course, when this pattern, everything is more easier because everything goes to the equilibrium 1. And so all the picture becomes blue because you reach again the stable equilibrium. Okay, yes, so now I think I stop here because the next point is about time varying solution. So yes. I think if you want, we can discuss if I went too fast on some point, and yeah. So
I think
question.
I don't know. I think it was great. You did the calculations. For me, it was very easy to follow. So, what about the students' comments?
For me, it was also very good. So maybe the students should speak.
So maybe I can explain what is the blue curve that I didn't show you exactly. So if you remember, if I go back to my equation, here. So here, so I have this extended Jacobian, which is J alpha, which is the G0 times lambda alpha times this matrix D. Spectrum matrix is endless, okay? But in principle, if you do this on a continuous support, is everything the same, except that you have to replace this part by say minus k square. So you are using periodic boundary conditions, so you use Fourier transform. So you have to replace this by the Fourier modes. So in some sense, this is a continuous variable.
Timoteo, we had a period where we lost.
Sorry.
So can you?
Okay. Yeah, I start again. Yeah, I start again. Okay. So what I mean is that I started by studying this extended Jacobian, which is J0 times this matrix D times this number lambda alpha. But lambda alpha is the spectrum of a matrix, so it's a finite number of numbers, is n numbers. Okay. Now you can do exactly all the same computation on a continuous support, say in 0, 1. And then indeed you think that the 0 is equal to 1, so you have a circle. Let's say you want to study Turing pattern on continuous support. If you do this, so using periodic boundary condition, everything is the same, but instead of the Laplace eigenvalues on the nectar, you have the eigenvalues of the Laplace operator, so the second derivative. And what is the eigenvalues of the second derivative? Is the minus the Fourier modes. Okay, and so minus the Fourier modes is a continuous variable, because in the continuous you can have this kind of so if instead of using here this lambda alpha, you use minus I wrote k, say kappa to the square, just remember this is the Fourier mode, then because kappa is a real number, okay, I got this figure where I have a continuous line. So the blue curve is nothing but the Turing behavior on a continuous support. And here we have an added value, which is the following. Because the network is symmetric, all the red dots stay exactly on the same curve that you should have found with the Turing pattern on the continuous medium. Okay, I will show you next time that if the network is not symmetric but is directed, this is not true. In the case of directionality, these dots go away from this line. And so in some sense, the continuous case of the symmetric network is the same, more or less. You can have some small changes, but it's the same. While continuous case, symmetric case, and directed case are different. And I will show you why. And just the last point, as I told you, the network is here. So now I can play with the network, and so I cannot play on the curve, the blue curve, because the blue curve is what the system tell me. But where I put the red dots is the network. So if you choose a network such that all the dots stay here, okay, then you will not have Turing pattern. So in some sense, you can control your network. You can decide which link to put or which do not put. And then you can move these red dots, so sliding them on the blue curves. And if you are able to put all them down, so in the negative part, then you remove the pattern. Or vice versa, if you want to have pattern, then you have to slide this point up to the point where you reach a positive point. So in some sense, you also have a way to control pattern on a network, just playing on the spectrum of the Laplace metric, which means playing with the network.
Very interesting, fascinating. How this would translate, going back to our epidemiological, how this can be, so isolating some city, this could play, for example.
Yeah, then so okay, what one can write, you can write, so the as I don't know how many states do you want to put, so at least SIR. So here you put the standard SIR model on node I, And then here you have to add the diffusion or the interaction. So because the interaction will be done next time, I suppose this is the diffusion. So then I mean that the rate at which S change in node I depends by some coefficient ds, which is the rate at which the susceptible person moves, times Lij Sj sum over j. This means that the number of or the concentration of susceptible person and node I increase because of the reaction, of course, but also because susceptible person from node J goes to node I. So this means that here you have your node I, here is node J. So each node is a city, and then you have a flow or susceptible person from I to J, from J to I, sorry. Okay, then you have the same equation for the other. So you have with some speed, infected people also move, and so you have this one, and then also you have the recover that also move. So this is really the basic mode. Sorry, J, the basic model that you could write. I think a better model would be one where indeed these quantities, these diffusion parameters are not constant, but depends on the state of the node. So I think a better choice would be, for instance, ds depends on the, so I don't know how to write exactly, but something like Si, Ii, and Ri. What I mean, it means that the susceptible person in node J, they will not go to node I if there are too many infected there, because they will got infection. So I think you have to, in some sense, put what I call diffusion coefficient inside the diffusion part and have something dependent on the state of the system. Again, it's not a problem because after all, Turing is close to equilibrium. So if you have this function, what you have to do at the end is just linearize close to the equilibrium. And so you will work, sorry, R, with some effective diffusive-like phenomena. But the idea is the same. Now the difficult part is that the reaction part, so the SIR model, does not admit a stable homogeneous equilibrium, except if there are only no, because so if you take the equilibrium 1, 0, 0, so sorry, all the persons are susceptible, you have 0 infected and 0 recovered. This equilibrium is stable if R naught is smaller than 1, or this positive is R naught, so it's stable, it's unstable. Where R naught is the ratio between the rate of production of S divided the rate of the recovering from I or death from I. Okay, and so this equilibrium is stable only if R naught is smaller than 1. But in any interesting epidemics, the case interesting is R0 larger than 1, because if R0 is smaller than 1, this means that the virus will die automatically without any intervention. While we are interested in case of COVID, at the beginning, R naught is large, is 2, 3, 4, 5 maybe. So you have to interact with the system, as I told you before, change the link in such a way your system becomes unstable. So you remove, you understand what I mean? So I think that a simple SIR model is not the good, the good part for the reaction part.
Yeah, what we observe, I have to check back, I will go back, but I remember that when we consider now that you can put, for example, COVID, or in the case of dengue, the seasonal effect in the beta, in the infectious parameters, so now becomes time dependent. Now, if it becomes time dependent, you can observe the phenomena that you related last time. Even something that eventually is stable dies off, it can have a transient that is not, is important. So it can accumulate, depending on the initial condition and depending on the phase, it can accumulate a lot of infected. So then you have the phase, you have a lot of other parameters. As soon as you put time dependence in the parameter, the problem becomes much richer because of this. The phase is important. It's not just R0.
Something that I didn't told you because, okay, I have no time to say anything. Okay, now let me check one of the pattern. Okay, this one. Indeed, you can estimate this path. So you can estimate which node will have a higher concentration and the ones that have lower concentration. And this depends. So this is not really the case, but assume that you have only one red dot, which is very high, and on the other very low. So this red dot is associated to one and only one lambda alpha. Then if you take the associated eigenvectors, lambda alpha, psi alpha, then this pattern reflects the entries of this vector. So here, so assume that you plot like these nodes, and then I put here UI. So this is the concentration of UI on each node. If on the same picture you plot the entries of this vector, then you see that this vector will have, I don't know, not exactly, but high, low, high, low, high, low, high, low. So there is a correlation between the entries of the eigenvector, the critical one, and the patterns. So this means that if you go back to your SIR model on a network, you can predict which cities will have, say, a larger amount of infected person by looking at the eigenvector, the critical one. And then if you want to remove this, of course, there will be hubs. Then you have to cut connection among links, among cities. And then you will move, in some sense, the spread of the information because of this correlation.
Very interesting. So it's worthwhile comparing the two models.
Yeah.
This is a linear and the ours, because ours the old one has non-linear model, no? But yeah, I think very interesting. Very interesting. So we should talk more about this. So I'm sorry, taking all the questions because I'm fascinated, but the students can please.
You are monopolizing, but there were good questions. It was very good.
I found it fascinating. So students, yes, question? Actually, I can stop